this example, we're going to be multiplying two power series. And we have this power series in red, which is n plus 3 all over 3n quantity factorial times x to the n. And the purple series is 4 to the n divided by the quantity 2n plus 3 times x to the n. Now, when you multiply these, we're going to multiply it just like we would if we were multiplying two polynomials that were finite. In this case, they're an infinite number of terms. And we can't really take the product of an infinite number of terms physically. So what we're going to do is we're just going to go out a certain amount of terms to make sure that we got everything that we need. Now this power series, we're going to go out to the fourth term, which means we're going to have our constant when n is 0, our x term, that's when n is 1, our x squared term when n is 2, and then our x to the third term, and that's when n is 3. We're going to take, well, first of all, just make sure you write out the terms of each of these series. Go out far enough. And sometimes it happens that you don't go out far enough and you realize, oh, I need a couple more terms. And then you just go back and add them in. Not a big deal. So I went out to n is equal to 4. And I listed all those terms here. And I did the same thing with purple. We're going to multiply this just as if we were multiplying two finite polynomials. So we're just going to use a distributive property where we take each of the terms and multiply it by each of the terms of the other polynomial. Now we can't really physically do that where we're finding every product for each term with an infinite number of terms, but we can go out far enough to complete our task. And our task is to find the product of these two series and go out to the fourth term. So that means when n is 0, that would give us our constant. When n is 1, we're looking for our terms that have an x in it. Then when our n is 2, we have x squared. And when x is 3, we have x to the third. So even though we're at x to the third here, we still have 4 terms because we're counting that constant. You can find your own method of doing it, but what I like to do is make a table. So I keep track of everything and I group them together. That way, when I go to add like terms, they're already grouped, easy to find, and I just add down that column. So now all we need to do, it's tedious, but it's easy. I take 3x to the 0 and multiply it by all of these. Then I take 2/3 x and multiply it by all of these. Then I take 5 over 720 and multiply it. And we just keep going as far as we need to. When I take 3x to the 0, I only need to multiply out to this term here, to the third. Because this is 3x to the 0, x to the third, when I multiply them together, that gives me an x to the third term. If I go any higher, then I'm going to get x to the fourth term, and we don't need that. So you just repeat that process. You take 2/3 x then and multiply it by each of these. You just stop until you get all the terms for x to the third. The last two terms you're going to end up multiplying is this term right here with the 1/3 x to the 0. If I go higher, that's going to give me an x to the fourth term. And then group them or organize it however you want. And then once you get it organized, you just add like terms. So you just add down the columns. Now, when I took the n equals 3 term from the red series and I multiplied it by the n equals 0 series, that gives me an x to the third. I can't go any further, or I don't need to go any further, I should say. Now, when I multiplied the term for n equals 3 of the red series, and I multiplied it by n equals 0 of the purple series, the number is super, super small where it gave it to me in scientific notation. Then once you have all your terms laid out, you group them together and add like terms, and your final answer is when you have all the terms combined, all the like terms combined, all the way out to the third degree.